Malik or Albert Fishman coming from Cavium, from the switching department of Cavium. And I would like to talk a little bit about the fabric role in the board in general and how programmable fabric can contribute and add value to board, and specifically what we do in Cavium-Xpliant and how we think that our silicon can move forward. So, and then honestly, I would like to have this discussion a little bit more interactive. I know it's 3 o'clock, people are tired, so if you have questions, you don't have to wait until then. Just feel free to stop me and ask any question. Okay. So let's start with the standard. I think that's the most classical, one of the first board slides. And one thing that, from hardware vendor standpoint, kind of bothers us is there's a lot, everything is virtual here, right? So there's lots of innovation, lots of interesting breakthrough ideas for virtualizing different services for core. But on the fabric side, on the hardware side, unfortunately, there's not too much innovation there, and the fabric today used most for connectivity purposes, right? And also the hardware itself is not really optimized to any of this. We have different flavors of the port, R port, D port, M port, and the fabric is like a one size fits all. If you look into actual deployments in production of different fabrics, it's not only about forwarding. Switch can do lots of other things, and actually these things are very useful for any fabric deployment. I mean, Core talks about bringing to a service provider environment all these concepts of agility and efficiency from data centers. If you go to data center deployments, what we see with our customers, so definitely forwarding, that's the main thing, but switch is not about moving packets from A to B. There's many other things that the switch can do, and in any typical deployment, production deployment, you'll find switches doing these things. Right? Another important point is that the core talks about the efficiency, and efficiency needs to be applied to the hardware as well. So if you go to a R port, E port, M port, and we dig a little bit deeper, each one of them has a little bit different requirements derived from their use case and can be applicable to the hardware. So we believe that programmable switches, this type of architecture, it allows actually truly software-defined SDN end-to-end solution, right? If you take fixed pipeline switches, traditional switches, they are maybe software-controlled, but definitely not software-defined. So I call them hardware-defined. You have, for example, in the Broadcom case, you have OFDPA, which is a kind of a hardware abstraction of, or OpenFlow abstraction of the actual Broadcom pipeline, but the software is not really able to go and change too many things there. So with programmable ASICs, you can truly implement software-definable network end-to-end, not only on the software side and the left side, but also on the hardware side. And I believe that, we believe that this combination of NFVs and software-defined networking on physical infrastructure, this is what will deliver the actual SDN premise of software-definable network. So a little bit about Cavium, what we have in production today. So we have today 3 types of, 3 families of devices that provide a wide range of different throughputs optimized to cost for different places in network. So our lowest end can go as low as 280 gig, and the higher end today can do up to 3.2 tera. We support all the interfaces, 1 gig, 10 gig, 25 gig, 40 gig, 50 gig, 100 gig, and each of these SKUs is optimized for, from cost standpoint and power standpoint to the actual deployment that needs this fit and speed. If I need to summarize briefly the value propositions that we are bringing as Xpliant, I can say that our products, we have 3 generations now, so it's built on a very strong hardware and software foundation, mature solutions that are being deployed in mega-scale data centers and many other carrier space. Plus, on top of this, supporting the standard functionality, our programmability actually allows to go and customize or drive-by software additions for specific use cases or specific deployments. A few words about our architecture. So we have here Zubian that drives all the software on our side, software implementation. So if we go schematically into our pipeline typical implementation, so we have Programmable Parser, where software can go and define different headers that to be parsed and further processed through the pipe. And then we have programmable units that can be combined in pipeline fashion to implement the packet processing. At the end of the pipeline, we have a packet rewrite that actually goes and modifies the headers, applies the changes to the headers. And we have also incorporate embedded traffic manager for all this, traffic scheduling and this kind of thing. The tables that we have on our ASIC, unlike a fixed pipeline ASIC, these tables are not pre-allocated, pre-dedicated to like layer 2, layer 3. So we have just a bunch of tables that can be used for exact match or for LPM, and we have also TCOM tables. And these tables per application need can be fields, the lookups can be defined by the software, by network operation system or the end user, and also the scale of these tables can be optimized and adjusted to specific implementation needs. So if we just summarize the differences between the legacy, the standard fixed pipelines, networking, pipeline processing, and our processing. So in traditional thing, the parser typically parses like standard Ethernet fields, while in our case, this is a very flexible. And just to give you an example, this is how our ASIC can support GTP, which is not non-Internet Ethernet standard, as well as the newer standards like a segmented routing. That when we actually taped out this chip, segmented routing wasn't something that is popular, but we support it now. The lookups are not hard-coded, but actually the tables and the lookup itself, the keys, are software definable. Modifications that can be applied on the packet also software definable. So basically, any permutations kind of allowed. Queues, we have a very strong traffic manager.
I have a question.
Sure.
I'm not a P4 expert, unfortunately, but this really looked like a lot P4 to me. And is this P4 or how is it different than?
So us and Barefoot actually is the same concept of the programmable switches. And this sense we are similar, right?
Similar, yeah.
And also
you have a similar architecture in here, as far as I see.
To some extent, the primitives are very similar. They also have a parser and this kind of blocks. Obviously, different ASICs, so there's some differences in architecture, but conceptually it's similar. Now, Barefoot they are promoting P4 as a software language to program their pipelines. We have our own language, Xpliant C, but at the same time we publicly endorse P4. We just P4 runtime. There was an announcement, and we also supported that one. So P4 that's something that we support as well.
So in this case, is it in C? You express your programming in C?
We define our pipeline is C type of language.
Okay. So it's not standard ANSI C, it's some variant of C.
It's called XPC.
The message that you're trying to deliver is that in order to get hardware level programmability, it doesn't have to be, could be any, it could be Broadcom, it could be Xpliant, it could be Barefoot.
So Broadcom, I have my, once they can comment, I think Broadcom is different, but as an Xpliant, we promote programmable switches that allows the application to go and define their own pipelines. Stuff, right? This is what.
This is definitely nice and the right architecture to go forward. So yeah, it's the GPU for network.
I like this. I like this comment. Now, P4 is how you go and implement. So we have our proprietary tools. But as the industry goes and adopts, broader P4, we support P4 as well.
Can you take P4 and compile to your Xpliant language?
That's a plan of action.
That's a plan of action.
So specifically with ONOS, whatever you integrate with P4 runtime, will support it as well at some point of time, and it's a little bit more mature.
So is the, I mean, the packet rewrite and SD modified logic over there also written in C-like language and compiled for your chips?
So let me answer that. So P4, and we fully endorse P4 as well as we are part of P4 org. The thing about P4 is if you look at P4 as a whole, it's an excellent language, excellent tool to support a specification for an ASIC. Okay. What we're talking about extending P4 runtime and other things. So P4 converted to XPC or P4 directly going through a set of compiler. So even if you look at Barefoot's architecture or P4 publicly available information, there is a language, parsing that language, parsing that specification into machine code, or net operator, just call it what the ASIC understands, is going through a compiler. That compiler has to support either one of them or both. So end of the day, you would have a specification. How do you express, how do you convert it to the language that your ASIC understands is the question.
Correct.
Okay. And that for that we have our compilers to support both.
Okay, so you're going to support P4 language? Or you're gonna stick with
We
your
do
own
endorse before what happens is it can be both ways, it can be done both ways, it's just there's no use case at this point to completely convert it from P4 to PC or something. And as Eric mentioned, the roadmap has P4 support for it.
Let me ask the question a different way. Do you feel that P4 as defined today has all the constructs that you need to express your pipeline?
I think it's a little bit different discussion. I think P4 16 is a step in the right direction, but obviously it needs to be evolved, and obviously I think it's a little bit more optimized to Barefoot ASIC, right?
But we were part of P4 initially, and from the early days. What we've seen P4 evolve at this point is exactly how we started out. So P4 initially started with one huge program where you define the whole switching pipeline, and that's how you express it. Our idea is to have, and you see our public information where you have engines, and you have expressions to define these engines. And you see P4 16 and all the latest P4 trends are coming towards that direction where you have different P4 engines or P4, I don't know what they call it, tar or profiles. Some templates that end up programming into the.
But I think the important point here is with programmable ASICs is, for the solution or other solutions, they can truly go and implement ASIC behavior, and also there are very limited resources on the ASIC optimized to their specific deployments. Now P4 or our proprietary tool, going through one compiler, another compiler, that's like, this is how we achieve it, right? And eventually, I think us as the Cavium will integrate our solution into the standard ecosystem. So if standard ecosystem chooses P4 runtime, we'll be there.
Okay. And your compiler supports your ASIC and not OBS maybe, or are you supporting OBS as well or other? Because in order to fully integrate it within core, you just don't have the fabric. You also have the plumbing, within the OpenStack environment.
So maybe you have that slide of.
Yeah, so I'll get to this in a couple of
before
slides.
you go there, let me quickly answer that, right? So might be
I mean, if it's covered, that's
okay. OBS, we don't use P4 or the pipeline to express into OBS. OBS is merely an agent that runs on a bare metal switch. So we use OBS as an OpenFlow agent to get into the core. So core messages are being core today or Trellix architecture today through ONOS only talks OpenFlow. Okay. They're talking about putting in P4 runtime or P4 as an expression to configure these switches, bare metal switches. That is where OBS comes in.
Yeah, I know. Yeah.
So P4 and OBS does not go for expanding. P4 is pretty much, or any compilation language will go and program the silicon, not the OBS part.
Okay. Any other question? Okay. So we believe that this type of architecture actually truly allows finally software-definable network solution, bringing physical infrastructure into this end-to-end model of SDN. And we believe our ASIC is the best fit for this one. Mature in production, supports all the primitives, works. So going into a little bit more details, like you asked, and we have also obvious slide following up. So in general, if we dive into our architecture, so we define something that we call it a pure OpenFlow pipeline profile, and it's nothing else but a bunch of stages, OpenFlow logical stages, and the tables associated with these stages, right? And we call it the Cavium Real OpenFlow Pro. That's our name. So this is how it looks like. And if you think about the architecture, it's very similar to the regional architecture of OpenFlow, right? Of having these stages and the tables. So for us, to support OpenFlow type of solution is very natural, very easy. On top of that, because everything is software definable, we allow a programmable way to extend forward pipeline or any other pipelines. The other difference is that in our case, you don't really need TTP. I call it software-defined networking versus hardware-defined networking. When you have, if you take a Broadcom as de facto the most dominant example, you take a Broadcom pipeline implementation that is exposed to OpenFlow, and you have to map your OpenFlow application to what Broadcom can support. So it's kind of hardware dictates. Right? So in our case, software can go and dictate.
So how do you handle the go-tos?
We do support go-tos.
You do support go-tos.
So
So you say you have simultaneous lookups, but how do you handle that with the go-to model that OpenFlow has?
So for our backend, there will be sequential lookups.
Right.
And there is also OpenFlow model where you have one OpenFlow lookup, which will say go to table 5 instead of going naturally to go to table 2.
Well, it wouldn't naturally go to table 2. The rule has to tell you what.
Yes, either the rule has to tell you, or rule says go out of the check.
Or go out of the check. You're done.
And that's where we support. All that is simple is just transferring to the next table.
So I think that
In this case, what your question is, how is Go to implemented, or your question is how can?
Well, you need to know what, when you say no TTP, it kind of strains credibility here, because you need to know what the match fields are that you're programming. You can't just make them up on the fly.
So I think what he meant, and correct me if I'm wrong, is by no TTP is that we don't have to dictate the TTP. The customer can bring their own
Sure.
table type package.
Right.
That's all we need.
But you have to understand what the tables are that you're using.
yeah, but,
All the
and
tables can have all tuples that you can.
I accept your comment. I can change from no TTP to no hardware dictated TTP or something
That
like
would
that.
be more accurate.
The difference is that we do not dictate the pipeline, right? TTP essentially defines pipeline. So we allow a NOS or port or user to go and define that pipeline. That pipeline for that application case becomes TTP. You can see it this way.
But you need to define the pipeline before you program it.
Yes.
The user will have. And in this case, the example is Trellis. Trellis defines the bunch of tables and what lookups they need to do for segment out.
But if you take a broader scope, if you take our implementations, we have the same ASIC that supports Trellis and supports implementations that are completely different.
Sure.
Right? So it's, even with say OpenFlow. We have also on the software side, I think that the way that we implement is allows very good performance in general in terms of the rules insertion, deletion, and this kind of things. The tables are the size of the table. It's also software definable. So you may want to have certain tables very small and other tables very big. And for different port, you may have different, residential port, enterprise, different tables and also different scale requirements. And also if you go between spine and leaf, also requirements are different, even if you use the same functions. So that's something that the software can define. In all these tables, the keys The table format is the software definable. And on top of that, we have also very advanced telemetry functionalities that we support. So we support, each table may have a counter, bind to a counter for debugging purposes, or this kind of things. As well as we support, so you can see.
Is that already in place, those functionalities? We're asking because we're in charge for ACORE and maybe.
So maybe Zuma can add, we say ACORE, it's on our roadmap, maybe you can add.
Yes, the trellis pipeline that we just discussed before this, yes it does.
Okay, so you're working with any brigade or?
We are working for the ONOS 112 release. So during the ONOS 112 release, we are our adapter. So there is an ONOS driver needed to be part of ONOS. So I don't know if there's a specific brigade for that at this point. It's 112 brigade.
So with ACORE itself, we haven't integrated with the collector and all the things that you have there. We take it step by step, right? So the next step will be to become part of ONOS distribution next release, and then we look into integration with ACORE.
Yeah, really glad to see you.
So we support all this, including customer definable, software definable counters. And the other things that we support also in-band telemetry, when you can take, the actual data packets and add the metadata. And we support embedded telemetry, the spec that Barefoot promote, as well as the ways that Broadcom and Cisco and others do it with OEM packets. For us, for telemetry, the metadata insertion and the transport there are kind of independent, so we can play. Right, so this is a generic view of our OpenFlow or a Cavium-Xpliant OpenFlow pipeline. And specifically for Core, as Joe mentioned, so Core already has in place today some kind of a pipeline. So we map that generic view into that specific pipeline with very minor changes, mostly on the group implementation. And we implemented that pipeline with 4 stages of OpenFlow. There is also a placeholder for 2 additional stages that the users can work. We can work with users and additional functionality there. So that's kind of a pre-announcement that we will be officially included in the next distribution of the ONOS, which is the version 1.12, going to be out in December. We support actually today, we have demonstrated that in MWC Americas in September, and the Zubin Trellis track was also showing a demo. So we support all this fabric-related standard applications. And from user standpoint, if you previously used the Broadcom switches, or any, I think today Broadcom is the only ASIC that has been supported in ONOS, the ways that you operate with the ONOS and the behaviors that you observe is the same thing, right? So from user standpoint, there is no change in his experience. And we started to push some documentation on the OpenCore, the wiki, just some kind of a high-level documentation. But by December, we'll push the full, right? We'll push the full documentation about our pipeline and what can be changed, and how it runs, and how to troubleshoot, and also we'll publish the tests that we support on this, so on. So everything will be there by December. Now, that's the slide that you were asking in terms of actual flow on the hardware box. So we have the ONOS as a SDN tutorial, and we contributed to ONOS our Xpliant driver, which actually kind of exposes the pipeline that we have implemented for Core, and essentially that everything that Core related is public, so that driver will be also publicly available. The interface to the actual switch is OpenFlow, and then the software that runs on the box itself, we have OVS that we use as an agent. So Broadcom, they use Indigo, we use OVS, but it's the same. It does the same job of dealing with OpenFlow protocol, and then it communicates with our SDK that will provide this binary for a port and with partners or customers that are under NDA, obviously we'll share all the sources. And the hardware that we use for port as a reference design, for reference code, is the edge core hardware. It's also, if you've seen Phil today presented in the Travis Track, the edge core hardware for port, so we also there.
You have a set of APIs already publicly available for the XP drivers. I mean, your driver APIs, are they available?
So the OS adapter does not need any open APIs at this point. The XDK, there are open APIs, set of open APIs.
They already published?
Yeah, we call it open XPS.
The OpenXPS is our variation to a OpenNSL. So we have all kind of APIs, including for a OpenFlow. Okay. So we believe that actually, this programmable functionality, can be used by port or other initiatives to design to operate for specific use cases, right? And I want to just throw a couple of ideas that we saw for each of these ports, what potentially can be done with our ASIC. So if some of these use cases are known, and there's a specific service providers that raise these demands. Some of them is just our ideas, and essentially, if there is a customer traction, we'll work with the Onos team to implement, because we can implement stuff on the ASIC side, but we need also collaborate with Rav and his team to implement functionality that involves this feature on the controller side. So for our port, a couple of things that we saw that there's a lot of things that are done in the server, right? If we take virtual OLT or specifically VSG functionality, everything is done by the VNet, right? But specifically, some cases you may not have, or even most of the customers, most of the subscribers don't really need service chaining. So if you could terminate a PVP over Ethernet, or sometimes it's a VLAN based, so you can terminate these services and provide some, couple of functions that the VSG is doing. The whole thing can be done at the Tor level, right? So you don't need to waste the server for this one, and also the processing will happen at terabit speed, right? At hardware speed. So we can do PVP over Ethernet as well as VLAN-based subscriber line termination for Q&Q or double VLAN support. We don't have. I know that the current solution has some kind of shortcomings. So in our case, we don't have any of these things. So we are able to provide full Q&Q support. By the way, I uploaded this slide in the PDM form to the website, so it's downloadable from there. It's not a confidential here. You can download it, right? So the other thing that we can do is for our port, we have enough scalability and enough flexibility to actually provide processing at per subscriber or per subscriber per service, right? So we can do QoS, we can do many other things at this level of granularity.
I have a question. So service chaining to cloud NFVs to be limited to the physical rack that I get.
That's what I saw from the Travis implementation today. I don't know if it's a hardware limitation or just Travis is not there. But what I've seen is that today actually everything needs to be in the same physical rack. I can double check this point.
So this comment is specific to our code.
We can do all this, security features like anti-spoofing when when the packet comes in and you want to change the IP.
From their perspective, we don't care. It's hardcore.
It's okay.
So we can do all the security checks because you can go and create non-standard non-Ethernet standard tables with lookup based on the source IP and something else, and to make sure that IP is actually correct, right? The security type of checks. The tables are very scalable. So just to give an example, we have another type of deployment when we scale routing tables for 1 million plus routes using just embedded memories, right? So, for offloading some of the routing tasks, we can create large tables for routing.
Your 10 minutes on. Your 10 minutes over.
I'm gonna start at 10 minutes.
Oh, okay.
Okay, I'll try to make it faster, okay? And maybe five more minutes. And the most important here, I think that in general in core, it's some kind of a new paradigm, right? And we all expect that if this core is going to be adopted by the industries, there will be new services and new use cases that hardware, software and hardware needs to support, or as a project needs to support. So we believe that on the hardware level, we have all the hooks and all the knobs to support all these new things that they may evolve. Now for M-Core, so we have demonstrated that the MWC M-Core racked by Cavium with, all these pieces are from Cavium. But on the fabric side, we are not married. I mean, obviously we want to promote, the more products from Cavium promote, the better. But if there are deployments that use x86, we will work with these deployments as well, because now fabric operation is kind of not related, right? And a couple of things that we have in mind is for virtual EPC functionality. Some of that functions can be offloaded to the hardware. We have a very sophisticated interactive QoS to provide services, personal application, security features. We can parse GTP tunnels and again extract the tunnel ID, subscriber ID, and provide different services. For eCore is kind of a new thing, but we are very flexible. And anything that's going to happen there, all these pseudo wires and EVPNs and this kind of things, our hardware will fully support, and we are flexible enough. I think that also for ePort, for all ports, but especially for ePort, observability to be able to see at the same time underlay and overlay headers is very important. This is something that we can do at the wire speed without kind of terminating packets and things like other solutions. So that's just briefly, I think that our offer is that we are fully compliant with core standard ecosystem, with tools, with standard application, everything works. Plus, our programmability and flexibility allows actually go and optimize solutions, specific use cases, or for future services to come. And we have also hardware, if there are some deployments that need 25 gig, I think that's basically the first part, hardware that supports 25 gig for more. A little bit of a high level of the roadmap, where we are going and where we think that the fabric needs to go is that today we have integrated with 1.12. All the basic things are there. One thing that we keep hearing is that troubleshooting is very important, so we have all these counters and other things that allows troubleshooting. This is where we are today. And going forward, I think that we will work with the community and the service providers and customers to go and optimize fabric behavior and scale to specific R-port, E-port, and M-port needs. We can, there is already work adding new features like PPP or return termination, this kind of things. So we'll support these features. Plus, there's also work to add A-port and all this telemetry capabilities. We are very interested. This is our point of strength. And I think that one thing that where we eventually, all the things may go is that our programmable ASICs are flexible enough to create something that they can be seen as application-defined for fabric, right? So we can run application and derive from that application the actual needs from the physical infrastructure, and then reload the physical infrastructure with a network profile, a network template that will be optimized to these needs. So I think that as a community, there is a long way to go there. But on the hardware side, as well as our SDK and integration, we support all these things. And for us, it's very important. We are a commercial organization. We want to work with customers. We want to support this phase in the core live when it transitions from POCs into something more real. And it's definitely, we invite all of you and the rest of the community to cooperate with us. So I have my email and We can also, with pseudonym. So please feel free to contact us, describe your use cases, talk to us about your needs, and we want to work with you and see how your needs can be fulfilled.
So one thing you can really do, maybe between Broadcom, you guys, and Barefoot, you can think about how loop 0 or collector level 0 can be implemented for sub 100 millisecond feedback loops. We can have some showcases or use cases.
Okay.
Great.
Thank you.
Thank you.